Hello everybody, today I'm going to explain what is a square wave. Alright, let's dive in. A square wave is a non-sinusoidal periodic waveform in which the amplitude alternates at a steady frequency between fixed minimum and maximum values, with the same duration at the minimum and maximum values. Clearly, as you can observe here and as we discussed in the previous video, this is not a sine wave. Sine wave follows the sine wave curve oscillation, and in this case, the wave is just switching, like from a maximum value to a minimum value almost instantaneously. Now, an ideal square wave, the transition between the maximum and minimum value is exactly instantaneous. But, that's just an ideal case. In real life, there is a slight delay. I'll explain the reason later in this video. Now, due to this transition, the square wave is often referred to as a binary wave. When you say binary, you just have two values, 0 and 1. And in this case, if we consider this region as 1 and this as 0, clearly the square wave is switching from 1 to 0 almost instantaneously. And then, after having spent some time in 0, it just jumps back up to 1 again. Also you can consider it as two states, off and on. A square wave is a special case of a pulse wave which allows arbitrary durations at minimum and maximum. In this case, this region is the maximum and this region is the minimum. And this region from here is a total period. So you can call this as a high period, low period, and total period. Now, the ratio of the high period to the total period is called as a duty cycle. A true square wave has 50% duty cycle, meaning the ratio of the high period to the total period is 50%, or in other words, the high period is same as a low period, which is why it's equal and hence the duty cycle is 50%. Now, square waves are often encountered in electronics, signal processing, digital signal processing, and digital electronics. They have a wide range of applications. Predominantly, they are used as clock signals because of their fast transitions between, on and off and 0 and 1, which is suitable for triggering synchronous logic circuit applications. A square wave is defined by the sine function of a sinusoid. So this is the sine function, and when the sine function is positive, the value is 1. When the sine function is negative, the value is -1, and the value of the function is 0 at the discontinuities of the transition. Now remember, a square wave is not a pure tone. A sine wave is a pure tone because it has only one single tonal frequency, where a square wave is an amalgamation of different sine waves, a lot of sine waves to be specific. So if you plot a frequency spectrum, you're going to see a bunch of frequencies. And this will be more intuitive when you take a look at the spectrograph, which I'll be sharing in a bit. Now let's listen to square waves of different frequencies such as 500 Hertz, 1000 Hertz, and 2000 Hertz, and I also studied their frequency spectrograph. This is a 500 Hertz square wave. Notice the large wavelengths, and this is how it sounds like. Alright, this is a spectrograph of a 500 Hertz square wave, and notice the peak here that's at 500 Hertz, and there are other frequencies as well, because square wave is a combination of multiple frequencies, and the frequencies are called harmonics or overtones, meaning they are integral multiple of the fundamental frequency, and the fundamental frequency is here the 500 Hertz. And square waves predominantly and only contain odd harmonics, meaning odd multiples of 500, meaning the next frequency is 1500 Hertz and the next afterwards is 2500 Hertz and so on. And you can observe here the decay of the harmonics is also minimal. And in musical terms, when you say you have a lot of high frequency content, the sound is going to sound much brighter, which exactly it sounds. This is a 1 kHz square wave. Notice the decrease in wavelength as the frequency is increasing, and this is how it sounds like. This is a spectrograph of a 1 kHz square wave, and the dominant of the fundamental frequency is 1000 Hertz, and the next frequency is like the next odd harmonic, which is 3000, and the next odd harmonic is 5000 and 7000 and so on. This is a 2 kHz square wave. Notice a decrease in wavelength, and this is how it sounds like. Alright, this is a spectrograph of a 2000 Hertz square wave. So as you can observe, the peak in this graph is 2000 Hertz and the next peak is the odd harmonic, which is 6000 Hertz and 10,000 Hertz and so on. Now a perfect or ideal square wave does not exist. Let's see the reason why. Let's consider this waveform. This waveform represents the displacement of air molecules. And let's say the molecule want to move from this point to this point. They can't just teleport. They need time to cover that distance. And this being the time axis, as soon as a molecule starts from this point, some time is going to elapse. And, the conclusion is that this line cannot be a straight line. It's going to take some time for the molecule to move, and it's going to be a slant line. But that, the time that it takes for the molecule might be in like nanoseconds or picoseconds. So it's almost zero, but, it's not exactly zero. Even in reality, when square waves are played through speakers, it causes the air to move very quickly, but it's just not instantaneous. Alright, thank you for watching this video. I hope you enjoyed it and learned something. Have a great day ahead.